All right, this is Chapter 8C, Conservation of Energy, and thanks again to Professor Tibbins. So here we have a waterfall in Yellowstone Park, and it provides an example of energy in nature. The potential energy of the water at the top is converted into kinetic energy at the bottom. So the objectives, define and give examples of conservative and non-conservative forces. Define and apply the concept of conservation of mechanical energy for conservative forces. Define and apply the concept of conservation of mechanical energy accounting for frictional losses. Potential energy is the ability to do work by virtue of position or condition. So here we have gravitational potential energy. So a mass is held a distance h above the Earth, and if released, the Earth can do work on the mass. So it's the gravity that's being caused by the Earth that can do work on the mass. And so the work would be mgh, and as we can see here, mg corresponds to the force, h is the displacement. So it's the same concept that we had before, we're just now giving it new names, mgh. So is this work positive or negative? Well, the thing is, if we say that what is the work being done by Earth, that's positive. But if we were to lift that mass and give it potential energy, the gravity would be doing negative work. So if it falls, gravity is doing positive work on it. Gravitational potential energy U is equal to the work that can be done by gravity due to height above a specified point. So U equals mgh is gravitational potential energy. Here's an example. What is the potential energy when a 10 kilogram block is held 20 meters above the street? We just plug in m is 10 kilograms, g is 9.8 meters per second squared, and h is 20 meters. So we get the potential energy is 1,960 joules. The origin of potential energy. Potential energy is a property of the Earth body system. Neither has potential energy without the other. So here we see a block being raised to a height h, and then it falls and it comes back down. So work done by lifting force F provides positive potential energy mgh for the Earth body system. So remember that the Earth is what's pulling down on that body, and it's by Newton's third law, the equal and opposite reaction force is the body's pulling up on the Earth. So only external forces can add or remove energy, and that means external forces to the system, in this case the block. The external force is the crane, it lifts it up and increases its potential energy. Conservative force is one that does zero work during a round trip. So here we have it going up and then it comes back down. So whatever work was done on the block by the crane gets converted to work done by gravity on the mass. So weight is conservative. Work done by Earth on the way up is negative mgh. Work on return is positive mgh. So the net work has to be zero. So that force, the force of gravity, is a conservative force. What about the spring force? The force exerted by a spring is also conservative. When stretched, the spring does negative work, which is negative 1/2 kx squared. On release, the spring does positive work, which is positive 1/2 kx squared. The net work is zero, so the spring force is conservative. Independence of path. Work done by conservative forces is independent of the path. So whether we take an incline all the way from A to C, or we go from A to B to C, the work done is equal because the gravitational field still has to go a height h. And it's also the same over here because U equals mgh. It's independent of the path, whether it went down the incline or whether it was lifted straight up. Because only the vertical component of the weight does work against gravity. So remember that the force has to be parallel to the displacement. What about non-conservative forces? Work done by non-conservative forces cannot be restored. Energy is lost and cannot be regained. It is path dependent. So if we have friction it would matter a lot whether we took two different courses. So if I went up the incline or just lifted it up, I would have different amounts of frictional loss, so it's non-conservative. Same thing here. As this thing oscillates back and forth, it's going to lose energy to friction until it just stays still. So frictional forces are non-conservative forces. Work of conservative forces is independent of path. So here we have a block going through from A to B to C back down to A. And if there's no friction, it doesn't matter which path it takes. So for gravitational work, there's zero net work, but for frictional forces, that's not true because the different distances give us different displacements, which means there's going to be different amount of work lost to friction. So the work done against friction is greater for the longer path BCD. So BC, suppose that could be D. So depending on the path, it's going to change the amount of work lost to friction. Stored potential energy. Work done by a conservative force is stored in the system as potential energy. So here we have a spring system. The potential energy is equal to the work done in compressing the spring. So F times X is equal to Kx to compress. F of X is equal to Kx to compress. The displacement is X. So the potential energy of a compressed spring is equal to the amount of work put into the spring, which is 1/2 Kx squared. Conservation of energy. In the absence of friction, the sum of the potential and kinetic energies is a constant, provided no energy is added to the system. So here we have potential energy up here, which is mgh. Now gravity can do work on it. So at the top, we have potential energy, but zero kinetic because it's not moving. We assume it starts from rest. And at y, it's going to have a combination of the two. Whatever velocity it has at that moment, it's going to contribute to the kinetic energy, and then the potential energy is going to be due to the height y. At the very bottom, there's no potential energy left, and all the kinetic energy has, and all the energy has become kinetic energy. So the total energy of the system remains constant. So constant total energy for a falling body. So at the top we have potential energy, and it's going to become kinetic energy at the bottom. So at y, we have it as a combination of potential and kinetic. At the top, it's just potential. And at the bottom, all that energy has become kinetic. So we have this at the top, this in the middle, and this at the bottom. The energy is always the same at any point, and again, we're neglecting air friction. Let's try this one. A 2 kilogram ball is released from height of 20 meters. What is the velocity when its height has decreased to 5 meters? So up here, it's going to have just potential energy, and then it's going to become potential and kinetic energy. So notice that when we set these equal to each other, here's the top, and here's at 5 meters. The masses cancel. And then we can write 2gh. So what we did is we multiply by 2 all the way across, and this becomes v squared. We can take this part and take it to the left, and this is where we get h minus y. And we can then calculate this out, which is 20 minus 5 is 15. And so the velocity at 5 meters above 0 is going to be 17.1 meters per second. This is the same as if we considered this the initial potential energy, mgh, and then this is the final spot. So in other words, we could have just set the initial potential energy, U equals mgh, to U equals mg times 15, because that's the difference, and then down here would be the final kinetic energy. Or we could do this. Either way works. A roller coaster boasts a maximum height of 100 feet. What is the speed when it reaches its lowest possible point? So we assume zero friction. At the top, it's all potential energy. At the bottom, it's all kinetic energy. So the total energy is conserved. So what we do is we set the initial potential energy equal to the final kinetic energy. The masses cancel, And we get this, which we could have also gotten from the kinematic equations for free fall. And so we got the maximum velocity is 80 feet per second. Again, the initial potential energy has to equal the final kinetic energy. Conservation of energy in absence of friction forces. The total energy is constant for a conservative system, such as with gravity or a spring. So whatever you have at the beginning, you shall have at the end. So this is for gravitational potential energy, and this is the spring's potential energy, and then this is the kinetic energy at the bottom. So we're going to use some combination of these. So height, spring, and velocity. Water at the bottom of the falls has a velocity of 30 meters per second after falling 35 feet. What is the water speed at the top of the falls? So again, another typo here. This should be meters because we have this as a height of 35 meters. And then water at the bottom of the falls has a velocity of 30 meters per second. So this should be second, not second squared. What is the water speed at the top of the falls? So at the beginning up here, it has nothing but potential energy. So we're going to assume that the height at the bottom is going to be 0. So we have the height, we have 35 meters. So we want to find the initial velocity. So water at the bottom of the falls, again, that's what we want to find. The bottom of the falls is 30 meters per second, and it falls 35 meters. So we have to choose an endpoint at the bottom of the falls. So the endpoint we're going to say is 0, and then the final velocity is going to be VF. So the total energy at the top has to equal the total energy at the bottom. At the top, it has potential and kinetic, and at the bottom, we're going to say it just has kinetic. Notice that the masses cancel, and the final potential energy is 0. So we get this equation right here. And it should look familiar because it's just rewriting the kinematic equation. And the way that we recognize it was VF squared equals V naught squared plus 2A and then D. In this case, A is G and D is H. So we can solve for V naught squared and then square root the number that we get there, and we get 3.86 meters per second. So the crucial part here is that at the top it has potential energy. It has an initial kinetic energy because the water is moving. At the bottom it has no potential energy and has a final kinetic energy at the bottom. After that we just solve for the unknown. Bicycle with initial velocity of 10 meters per second coasts to a net height of 4 meters. What is the velocity at the top, neglecting friction? So the energy at the top has to equal the energy at the bottom. At the energy at the top, it has potential and kinetic. And at the bottom, he just had kinetic energy. There was no height. So now we set the top equal to the bottom. The masses cancel. We can multiply everything by 2 and solve for the final velocity, in which case we get 4.65 meters per second. So how far up the 30-degree incline will the 2-kilogram block move after release? The spring constant is 2,000 newtons per meter, and it is compressed by 8 centimeters. So we have to figure out how much energy is stored in the compressed spring, and all that energy is going to be turned into kinetic energy, and at the very top is going to be just potential energy. We also have to figure out the height. We know the compression is going to be 8 centimeters, so we have to change that to meters. So at the beginning we have no gravitational potential energy. We'll say we'll start that at 0. It just has the spring's potential energy, and all that is going to become the gravitational potential energy. So as it goes up, that kinetic energy is going to be turned into gravitational potential energy. So by conservation of energy, we have that the stored energy in the spring has to become the gravitational potential energy. And solving for the height h, we see that it's going to go 0.327 meters up. But maybe we want to find out how far it went up the incline. In that case, we have to use the angle here of 30 degrees. And we notice that h is on the opposite side and s is the hypotenuse. So we can use the sine of 30 and solve for s. In this case, it would be 65.3 centimeters or 0.653 meters. Energy conservation and non-conservative forces. The work against friction forces must be accounted for. Energy is still conserved but not reversible. So conservation of mechanical energy. We're going to have the initial potential and kinetic energy is going to equal the final potential and kinetic energy plus any of it that's lost to the work done by friction. So read the problem, draw and label and sketch. Determine the reference points for gravitational and or spring potential energies. Select a beginning point and an ending point and ask 3 questions at each point. Do I have height? In that case, I use gravitational potential energy. Do I have velocity? In which case, there's kinetic energy. Do I have a spring? In that case, I have the spring's potential energy. Apply the rule for conservation of energy. And remember to use the absolute value of the work of friction. So let's try one. A mass m is connected to a cord of length L and held horizontally as shown. What will be the velocity at point B? So at this point we have gravitational potential energy, and this is the height that it's going to go. It's the height L. It's going to come back around here and it's going to swing around here to this height right here. Notice that this height is 2r. So the change in the height from here to here is just L minus 2r, which we can call D. So we draw and label. Begin at A and end at B. And then our reference point right here is going to be that the gravitational potential energy is 0 there. So this is the maximum kinetic energy here. And applying conservation of energy. There's no frictional loss, so that's 0. So at the very top, it's mgl. There's no kinetic energy. We assume it starts from 0. And then the potential energy is going to be mg2r, which is this part right here, 2r. And it's going to have a kinetic energy 1/2 Vc squared. The m's cancel. And then we can multiply by 2. And then we can solve for Vc, but we need to find out what R is. So we know what L is, it's 20, and then D is 12. So if we take the difference between them, we can figure out that R is 8 meters. So plugging in everything that we know and square rooting it, we can figure out what the velocity is at C. So again, the basic idea is this potential energy becomes this potential energy and this kinetic energy. Another way we could have done it is just found out the difference in the height here. This would have been our potential energy and this would have become our kinetic energy. And we could have also done that too. And you see that the real change in height here is actually just going to be, so if R is 8 meters, then this is 16 meters. L is 20, so the difference that it went down is 4. And you can kind of see that right here. So it's 20 minus 16, which is just 4. So let's try this one. A 2 kilogram mass M located 10 meters above the ground, so here's our H, compresses a spring 6 centimeters. To change that to meters, the spring constant is 40,000 newtons per meter, and the coefficient of kinetic friction is 0.4. What is the speed when it reaches the bottom? So it's going to have the spring pushing it down and also gravity pushing it down, but friction is going to go against it. So here's friction in the opposite direction, the normal force. Here's a component of weight. And so we're going to have beginning at end. So by conservation of energy, we have the initial potential energy, and we have the stored energy in the spring, and that's going to equal the final kinetic energy plus any of the work done by friction. The work done by friction is the force of friction times the displacement x, which in this case is given by s. Remember, it's mg cosine theta. And so we have the potential energy plus the energy stored by the spring has to equal the final kinetic energy and the work done by friction. We can use the angle and the trigonometric function of the sine to find out that this displacement here, which before was denoted by s, which is now x, is 20 meters. So now I can find out the work done by friction. So here it is 136 joules. So I took my coefficient of kinetic friction times my mass times my gravity, and then this was the cosine of 30 times the displacement, which was x, 20 meters. So here is my initial potential energy, and again it's the 10 meters. And then I can find my energy stored in the spring, which is 1/2 k x squared, which is 72 joules. So now I have all these pieces and I can find my kinetic energy. So notice this is negative here. So what happened is this one moved over here, and so it became negative. So I have the final kinetic energy equals the initial potential energy plus the initial potential energy stored in the spring minus the work done by friction. So these add together and you subtract the work done by friction, and I have 132 joules. But I know the mass, and I know that this is 1/2, so those cancel. And so I just square root the 132 to get 11.4 meters per second. So again, conservation of energy at the top has potential, gravitational potential energy. The spring is compressing it, so as stored energy in the spring, when it goes all the way down, it's going to have a final kinetic energy, and it's going to lose some energy due to the work done by friction. So gravitational potential energy, U equals mgh. Spring potential energy is 1/2 kx squared. Kinetic energy is 1/2 mv squared. And the work done by friction is F